Alkane oxidations. First one, methane treated with O2 in the presence of copper, temperature 523 Kelvin, pressure 100 atmospheric pressure. The methane will be converted to methanol. Suppose if I take ethane, the ethane methyl group converted to corresponding ethanol. So here the reagent is copper, temperature 523 Kelvin and pressure 100 atm. Second reaction, methane when treated with O2 in the presence of molybdenum oxide, the methane carbon will be converted to aldehyde. Suppose if we take ethane treated with O2 in the presence of molybdenum oxide, the methyl group will be converted to CHO. It is a acetaldehyde. Third reaction, ethane when treated with O2 in the presence of manganese acetate, the terminal methyl group converts into carboxylic acid. Suppose propane treated with the same reagent converts the propane methyl carbon converts into corresponding propionic acid. CH3 group converts into COOH. It is a propionic acid. Alkane with tertiary hydrogen. If the molecule has tertiary carbon which is having tertiary hydrogen, if it is treated with KMnO4 or K2Cr2O7, at this tertiary carbon we get tertiary alcohol group. Second example, it is tertiary carbon. So simply we write the answer at tertiary carbon. Simply we write the OH group. Next example, this is a tertiary carbon and simply we connect the OH group. Next example, there is no tertiary carbon, it is primary carbon, secondary carbon, primary carbon. So we have to consider no reaction. Next molecule, it is a quaternary carbon, primary carbon, secondary carbon, and secondary carbon. So there is no tertiary carbon, that's why there is no reaction. Therefore, alkanes with tertiary hydrogens only react with KMnO4 or K2Cr27 and finally gives corresponding tertiary alcohols. So finally they give corresponding tertiary alcohols. Ozonolysis. When alkene treated with ozone followed by zinc H2O or zinc acetic acid or triphenylphosphine or dimethyl sulfide, so this reaction is known as reductive ozonolysis. In the reductive ozonolysis, simply we have to break the double bond and we have to attach the two oxygens both sides. Therefore, the corresponding products are double bond O and C double bond O. Here the remaining groups are R. So in this case, according to alkene, we are getting the ketones. We are getting the mixture of ketones. When alkene treated with O3 followed by H2O or H2O2 or Ag2O. So this ozonolysis is known as oxidative ozonolysis. In the oxidizing agents, this ozonolysis takes place. So in oxidative ozonolysis, we have to dissociate the double bond and we should write the corresponding answer keto group and another one also keto group. Both are keto groups. So simply here in the reductive ozonolysis, we have to break the double bond, add oxygen. In the oxidative ozonolysis also, we have to break the double bond and add oxygen. Next example, when the alkene treated with ozone and zinc H2O, zinc acetic acid, triphenylphosphine, dimethyl sulfide, it is reductive ozonolysis. So in the reductive ozonolysis, we have to break the double bond and add oxygen to the corresponding carbons. Therefore, we get corresponding ketone and another one the corresponding aldehyde. First compound is ketone, second compound is aldehyde. When alkene treated with ozone, H2O, H2O2 or Ag2O, this reaction is known as oxidative ozonolysis. In oxidative ozonolysis, we have to break the double bond and write corresponding product, and this will be converted into corresponding ketone, and it will be converted to, because of CH bond, it gives corresponding carboxylic acid. Because of CH bond, it gives corresponding carboxylic acid. Therefore, left one is ketone and right one is carboxylic acid. In the reductive ozonolysis, we get the mixture of ketone and aldehyde. In the oxidative ozonolysis, we get the mixture of ketone and acid. When alkene treated with ozone, zinc H2O, zinc acetic acid, triphenylphosphine or dimethyl sulfide, it is reductive ozonolysis. In the reductive ozonolysis, we have to dissociate the double bond and this portion will be converted into aldehyde. Simply add oxygen in the reductive ozonolysis and this portion will be converted into aldehyde. So in this case, we are getting the mixture of aldehydes. In the second example, when alkene treated with ozone followed by H2O or H2O2 or Ag2O, so it dissociates and this portion will be converted into carboxylic acid because of CH bond, carboxylic acid, and because of CH bond it will also converts into carboxylic acid. So here we are getting the mixture of carboxylic acids. When ethene treated with ozone followed by zinc H2O, zinc acetic acid, triphenylphosphine and dimethyl sulfide, it is known as reductive ozonolysis. So in the reductive ozonolysis, we have to break the double bond and add oxygen. Therefore, corresponding product is CH2 double bond O, CH2 double bond O. When ethene treated with ozone followed by H2O or H2O2 or Ag2O, so alkene undergo ozonolysis. Because of the CH bond, it will be converted to formic acid, and because of the CH bond, the right side CH2 group also converts into formic acid. So in this case, we are getting mixture of formic acids. When alkene treated with ozone, zinc H2O, zinc acetic acid, triphenylphosphine and dimethyl sulfide, it undergo reductive ozonolysis, and here two double bonds undergo reductive ozonolysis. So simply here we have to add oxygens like this. So after dissociation of bond, we are just simply adding the corresponding double bond O. So it is a reductive ozonolysis. When the same compound treated with ozone followed by H2O or H2O2 or Ag2O, it is known as oxidative ozonolysis. In the oxidative ozonolysis also, we have to dissociate the double bond. and because of the CH bond this carbon undergo oxidation further, and because of CH bond this carbon also undergo oxidation further. Therefore the corresponding structure is, it is a keto, and this carbon is converted into carboxylic acid because of COOH. Now this portion we are writing carboxylic acid, below the plane methyl, double bond O, methyl. So in this case also we are getting the mixture of carboxylic acids with keto position in the, with the keto group in the beta position. It is a alpha alpha beta. So it is a beta keto carboxylic acid, beta keto carboxylic acid. When the triene treated with ozone followed by zinc H2O, zinc acetic acid, triphenylphosphine and dimethyl sulfide, it undergo reductive ozonolysis. So here simply we have to dissociate the double bond and we have to add oxygen at corresponding places. Therefore, this portion we can write like this. So simply we have to add double bond O. Simply we have to add double bond O. And this portion also converts into double bond O, double bond O, double bond O. So it is a final product. The same compound treated with ozone followed by H2O, H2O2, Ag2O, it is called oxidative ozonolysis. So in this case also we have to dissociate the double bond, but here the CH bond is present. Here the CH bond is present. Therefore corresponding answer, so the upper portion we can write like this, below the plane methyl, it is ketone, and because of CH bond here we have to write COOH, and because of CH bond here we write COOH. And the bottom part we can write like bottom part we can write here C double bond O, because of CH bond here COOH, because of CH bond here also COOH. Benzene treated with ozone followed by zinc H2O, zinc acetic acid, triphenylphosphine, dimethyl sulfide. So we have to dissociate the all the pi bonds and we have to add oxygen at the corresponding carbon. Therefore, we get corresponding compound 3 moles of CHO single bond CHO. It is called glyoxal. It is called glyoxal. Suppose benzene treated with O3THF, H2O, H2O2, Ag2O. So in this case also we have to break the corresponding C double bond C, but because of the CH bond, because of the CH bond, further oxidation possible. Therefore, we should write COOH single bond COOH. It forms 3 moles and it is a oxalic acid. It is a oxalic acid. The reactant is xylene. So xylene has two canonical structures. So here we have to consider two canonical structures and we have to do the ozonolysis for the two canonical structures. Suppose xylene treated with ozone followed by zinc H2O, zinc acetic acid, triphenylphosphine and dimethyl sulfide. Simply we have to break the double bond like this. So because of this one we get three compounds. Suppose it is A, it is B, it is C. Structure of A is CH3, C double bond O, CH double bond O. Structure of B is again CH3, C double bond O, CH double bond O, and the structure of C, CHO, CHO. And we have to do similar case in another canonical structure. Suppose it is E, F, G. So structure of E is CH3, C double bond O, C double bond O. CH3, structure of F, CHO, CHO, structure of G, CHO, CHO. So whenever the resonance molecule is coming, so we have to consider the resonance structures of corresponding benzene also. Now here in this case, if we observe, we are getting these two compounds are similar, and this is single compound and it is three compounds. So here 3 moles we are getting, here 2 moles we are getting, here 1 mole we are getting. So we are getting these type of compounds in 3:2:1 ratio. And octoxylene again treated with ozone or and followed by H2O, H2O2 or Ag2O. So simply here we have to break the bond like this. But if CH bond is present, because of the CH bond, we have to consider further oxidation also. So in this case, it is a A, it is a B, it is a C. So structure of A, CH3, C double bond O, COOH. Structure of B, CH3, C double bond O, COOH. Structure of C, COOH, COOH. Similarly, in the second molecule also we have to consider ozonolysis. Suppose it is a E, F, G. Structure of E, CH3, C double bond O, C double bond O, CH3. Structure of F, COOH, COOH. Structure of G, COOH, COOH. So in this case also we are getting 2 moles of this type of compound, 1 mole of this type of compound and 3 moles of oxalic acid. 3 moles, 2 moles, 1 mole. So these are the few examples of reductive ozonolysis and oxidative ozonolysis of alkene. When alkene treated with KMnO4 heat H plus or OH minus or in the presence of K2Cr2O7 H+, we have to break the corresponding CC bond. We have to break the corresponding CC bond and we have to oxidize the corresponding carbon. So it is a ketone carbon and it is also ketone carbon. Both are ketone carbons. Next, when the alkene treated with cold alkaline KMnO4, it is also known as Bayer's reagent. KMnO4 0 degrees Celsius, that means cold KMnO4, OSO4, osmium tetroxide, sodium bisulfate, water. Any one of these combination, here syn hydroxylation takes place. Syn hydroxylation takes place. That means a double bond, simply we have to add two OH groups from the same side. But here stereochemistry not important. In this case, stereochemistry not important in this reactant. Simply we can add two OH groups. When alkene treated with peroxy acid, this reaction is known as epoxidation. Epoxidation. Addition of oxygen takes place from the same side. That's why it is a syn epoxidation. So simply what we have to do, we have to remove the pi bond. We have to remove the pi bond and add oxygen like this. We have to remove the pi bond and add oxygen like this. Next, alkene treated with peroxy acid water. Peroxy acid water. This reaction is anti-hydroxylation. This reaction is anti-hydroxylation. So here what happens? We have to add two OH groups. Two OH groups opposite side. Here OH group, here OH group. So this is an example of anti-hydroxylation. Now, one alkene without hydrogen, one alkene with hydrogen. If this kind of reactant treated with KMnO4, heat H plus or OH minus, or potassium dichromate H plus, simply we have to break the CC bond, and the left group will be converted to keto, and the right group, because of CH bond, it will be converted into carboxylic acid. Carboxylic acid. Second one, an alkene treated with cold alkaline KMnO4 bears reagent KMnO4 0 degree Celsius, cold KMnO4, OSO4, NHSO3, water. So here the double bond react with the corresponding reagent, and this reaction is syn hydroxylation. Syn hydroxylation. So simply we have to remove the pi bond and add two OH groups at this carbon OH group and at this carbon OH group. Okay, so here it is a sp3 atom connected to four different groups. Therefore, OH can be added from the above the plane, from the below the plane. In terms of optical isomerism, it is a chiral center. It is a chiral center, and we get two configurations. One is R configuration, one is S configuration. When the alkene treated with peroxy acid, this reaction is known as epoxidation. Epoxidation. So simply what we have to do, we have to remove the pi bond and add oxygen. We have to remove the pi bond and add oxygen. It is simply epoxidation. So addition of oxygen takes place from the above the plane, from the below the plane. When the same alkene treated with peroxy acid and water, peroxy acid and water, this reaction is anti-hydroxylation example. Anti-hydroxylation. So remove the pi bond and add two OH groups. Remove the pi bond, add two OH groups. So we can add two OH groups. Again, it is a only chiral center. So peroxide can attack both sides. That's why we get two possibilities. It is chiral center, R configuration plus S configuration. Both are possible. That means OH we can write above the plane, we can write below the plane. It is not sp3 atom connected to four different groups. It is not chiral center. That's why there is no need of stereochemistry, but here stereochemistry is important. It is a cis alkene. Cis alkene treated with the KMnO4 heat H plus or OH minus or potassium dichromate H plus. So simply we have to break the CC bond. Because of CH bond it undergo oxidation. Because of CH bond it undergo oxidation. So left group, because of CH bond you can write COOH. Right group, because of CH bond we can write COOH. Next, cis alkene treated with cold alkaline KMnO4 bears reagent KMnO4 0 degree Celsius, cold KMnO4, osmium tetroxide, sodium bisulfite, water. This reaction is an example of syn hydroxylation. Syn hydroxylation. It is a cis compound, syn hydroxylation. We get meso type of compound or erythro type of compound. Meso type of compound or erythro type of compound. And how to write the product? Simply to write the answer directly, we take these two groups in the vertical position. These two groups in the vertical position. It is the first carbon, second carbon, first carbon, second carbon. So these are alkene carbons. These are alkene carbons. Since it is a syn hydroxylation and meso type of compound, so if you want to write the meso, you should write the adding group same side. So this molecule is formed, suppose if the reagent attacked above the plane, and this molecule is formed if the reagent attacked below the plane. Two possibilities. And the remaining carbon having the hydrogen. Remaining carbon having the hydrogen. In this case, these two molecules are same, because if you rotate the molecule like this, we get the same compound. So finally you are getting the meso type of compound. Finally, you are getting the meso type of compound. Cis alkene, syn hydroxylation, meso. Next, when cis alkene treated with epoxide peroxyacid, this reaction is epoxidation. It is a syn epoxidation. Simply we can write the answer like this: syn epoxidation. Next, when cis alkene treated with the peroxyacid and water, it undergo anti-hydroxylation. It undergo anti-hydroxylation. And how to write the answer? Simply, it is a cis compound, anti-addition. So we get trio type of compound: CAT cat, CAT cat, trio type of compound. And how to write the answer directly? These two R groups vertical. These two R groups vertical. Alkene first carbon, alkene second carbon, alkene first carbon, alkene second carbon. So in the trio type, we have to add OH group opposite side. We have to add OH group opposite side. So the first compound is formed because of above the plane attack. Second compound is formed because of below the plane. So it is a simply, we can write mirror image type. And the remaining groups are hydrogens. Remaining groups are hydrogens. So this is the, these two compounds are non-superimposable mirror images. Non-superimposable mirror images. So it is a enantiomer 1, it is a enantiomer 2. And because of the reaction mechanism, two are forming almost equally. 50% enantiomer 1 because of above the plane attack, 50% below the plane because of below 50% enantiomer 2 because of below the plane. Therefore, overall we are getting racemic mixture. Overall we are getting racemic mixture. It is a transalkene. Transalkene treated with the KMnO4 heat H plus or OH minus K2Cr2O7 H plus. So simply we have to break the CC bond. Because of CH bond, the corresponding carbon converts into carboxylic acid. Because of CH bond, the corresponding carbon converts into carboxylic acid. The second one, transalkene treated with Bayer's reagent, cold alkane KMnO4, KMnO4 0 degrees Celsius, cold KMnO4, peroxy acid, sorry, OSO4, NHSO3, water. So this reaction is an example of syn hydroxylation. Syn hydroxylation. So trans compound, syn hydroxylation, trans compound, syn hydroxylation. We get trio type of compound. Trio type of compound. So how to write the trio type of compound? How to write the trio type of compound? These two groups vertical position. These two groups vertical position. Trio means opposite. Suppose this product is formed because of above the plane attack, and this product will be formed because of below the plane. Above the plane ఒక కాంపౌండ్ ఫామ్ అయితే below the plane mirror image తీసుకోవాలి. And remaining carbon having hydrogen groups. So this is enantiomer 1, enantiomer 2, enantiomer 1, enantiomer 2. Both are forming equally. That's why it is also racemic mixture. That's why it is also racemic mixture. When the alkene treated with peroxy acid, this is epoxidation. Syn epoxidation. So we get simply corresponding epoxide. We get corresponding epoxide. Transalkene treated with peroxy acid water. This is an example of anti-hydroxylation. This is an example of anti-hydroxylation. Trans compound, anti-erythro type of compound. Trans compound, anti-erythro type of compound. So in this case also we should write the molecule like this. These two R groups in the vertical position. These two R groups in the vertical position. Erythro means same side. Erythro means same side. So first molecule is formed because of above the plane attack. Second molecule is formed because of below the plane attack. So we should write two hydrogens like this. So it is a, in this case, if you rotate the second compound, because of the structure, we are getting same compound, and it is a meso type of compound. It is a meso type of compound. Trans compound syn hydroxylation trio, trans compound anti-hydroxylation erythro, trans syn trio, trans anti-addition erythro. Cyclohexene, when treated with KMnO4 heat, KMnO4 H plus, KMnO4 OH minus, or potassium dichromate in the presence of acidic medium, so CC bond breaking takes place, and because of CH bond, it will be converted to acid. Because of CH bond, it will be converted to acid. Therefore, both carbons will be converted to acid. These two carbons will be converted to acid. Next, cyclohexene treated with cold alkaline KMnO4 Bayer's reagent, KMnO4 0 degree Celsius, cold KMnO4, OSO4 NHSO3 water. So this reaction is an example of syn hydroxylation. Syn hydroxylation. So simply at double bond, we should write the two OH groups same side. Two OH group same side. Syn hydroxylation. It is above the plane attack and it is below the plane attack. Above the plane attack and below the plane attack. And about the, if you rotate the molecule about this axis, we get the first compound. Therefore, both are same. In this case, both are same. It is also meso type of compound. When alkene treated with peroxy acid, it is a syn epoxidation. Syn epoxidation. So simply we have to add oxygen to the corresponding CC bond. When alkene treated with peroxy acid water, it is anti-hydroxylation. It is anti-hydroxylation. So simply we have to add two OH groups opposite side. Simply we have to add two OH groups opposite side. Simply we have to add two OH groups opposite side. When alkene treated with KMnO4 heat, either H plus or OH minus or potassium dichromate acidic medium, so we have to break the two double bonds. Even though they don't mention number of equivalents, we have to consider this reagent excess, and because of CH bond it undergo complete oxidation, and because of CH bond this also undergo complete oxidation. So the above portion we can write like this: double bond O COOH, and the below portion we can write like this. Below portion we can write like this. When alkene treated with cold alkane KMnO4 Bayer's reagent, KMnO4 0 degree Celsius, cold KMnO4, OSO4 NHSO3 water, this is syn hydroxylation. Syn hydroxylation. And here two double bonds are present. Therefore, if we take one equivalent, less sterically crowded alkene will react. So two alkenes manakunte less sterically crowded alkene will react. So this is less sterically crowded, it is more sterically crowded. Here I am ignoring the stereochemistry, so simply we can write the answer. It is a less sterically crowded. You can add simply OH groups. We can add simply OH groups. It is a syn hydroxylation with the corresponding reagent. When alkene treated with peroxy acid, it is a syn epoxidation, syn epoxidation, syn epoxidation, and in this case, electron density is important. Electron density more, electron density more reactive. Therefore, here electron density more and here electron density less. Therefore, corresponding answer, this alkene will be reacted. More electron density alkene will be reacted. Next one, anti-hydroxylation. Next one, anti-hydroxylation. So anti-hydroxylation also, if two alkenes are present, electron density more alkene will be reacted. Therefore, this alkene will react, and here I am ignoring the stereochemistry. So simply we can write two OH groups. Simply we can write two OH groups. It is an example of anti-hydroxylation. When alkyne treated with ozone followed by zinc H2O, zinc acetic acid, triphenyl phosphine, dimethyl sulfide, it is reductive ozonolysis. In the reductive ozonolysis, we have to write simply it is a triple bond. So at the triple bond position, we should write diketo form. At, at the triple bond, we should write diketo form. It is a alpha diketo. With respect to one CO, another carbon is alpha. Alpha diketo molecule. When the same alkyne treated with ozone followed by H2O, H2O2, Ag2O, it is known as oxidative ozonolysis. In the oxidative ozonolysis, we have to break the triple bond completely and both molecules will be converted into carboxylic acids. Both molecules will be converted into carboxylic acids. When the alkyne treated with cold alkaline KMnO4, it is also known as Bayer's reagent. It is also known as Bayer's reagent or KMnO4 0 degree Celsius or KMnO4 273 Kelvin. So the triple bond carbons will be converted into diketo form. The triple bond carbons will be converted into diketo form. With respect to CO, it is a alpha. Therefore, it is a alpha diketo molecule. Alpha diketo molecule. In the same alkyne treated with KMnO4 heat, KMnO4 heat, KMnO4H plus, KMnO4OH minus, and K2Cr2O7H plus. So in this case, here we have to break the triple bond completely and both molecules will be converted into carboxylic acids. Both molecules will be converted into carboxylic acids. When terminal alkyne treated with ozone followed by zinc H2O, zinc acetic acid, triphenyl phosphine, dimethyl sulfide, it undergo reductive ozonolysis. In the reductive ozonolysis, simply we should write wherever the triple bond is present, we should add double bond O two times and it is a alpha keto aldehyde. With respect to CHO, it is alpha carbon. Therefore, it is a alpha keto aldehyde. Alpha keto aldehyde. And the terminal alkyne treated with ozone followed by H2O, H2O2 and Ag2O, it undergo oxidative ozonolysis. In the oxidative ozonolysis, we have to break the triple bond and left molecule will be converted to carboxylic acid and right side carbon will be converted to formic acid. Converted to formic acid. When the terminal alkyne treated with cold alkaline KMnO4, which is Bayer's reagent, or KMnO4 0 degree Celsius or KMnO4 273 Kelvin. So here at the triple bond position, so it will be converted to R C double bond O COOH. The last carbon will be converted into carboxylic acid. The last carbon will be converted into carboxylic acid. It is known as alpha keto acid. It is alpha keto acid. When terminal alkyne treated with K-4 heat, K-4 H plus, K-4 OH minus, K-4 H, K2Cr2O7 H plus. We have to break the triple bond and left molecule will be converted to formic acid, and right side carbon initially it forms formic acid, but it again converts into CO2. So the final product is CO2. So here the final products are these two. So formic acid is not final product. Final product is carboxylic acid and CO2. When alkyne treated with it is also acetylene. This molecule also acetylene. When acetylene treated with ozone followed by zinc H2O, zinc acetic acid, triphenyl phosphine and dimethyl sulfide, it is reductive ozonolysis. So simply wherever the triple bond is present and both carbons will be converted into corresponding carbonyl compound. So this molecule is known as glyoxal. When acetylene treated with ozone followed by H2O or H2O2 or Ag2O, so it undergo oxidative ozonolysis. In oxidative ozonolysis, we have to dissociate the triple bond and both carbons will be converted to formic acid. When acetylene treated with cold alkaline K-4 or K-4 0 degree Celsius or K-4 273 Kelvin, so both carbons will be converted into carboxylic acids. Without dissociation of CC bond, both carbons converted into carboxylic acids. It is known as oxalic acid. It is known as oxalic acid. When acetylene treated with K-4 heat or K-4 H plus or K-4 OH minus or K2Cr2O7 H plus, so here the acetylene triple bond undergo dissociation and both carbons will be converted to CO2. Both carbons will be converted to CO2. Primary alcohol to aldehyde RCH2OH. It is a primary alcohol. Primary alcohol. If it undergo oxidation, initially it forms aldehyde and then finally it converts into carboxylic acid. So primary alcohol can be oxidized to aldehyde and carboxylic acid. So it is a mild oxidation. Primary alcohol to aldehyde is mild oxidation. It is a mild oxidation. Now we are writing the reagents for mild oxidation. That means primary alcohol conversion to aldehyde. Primary alcohol conversion to aldehyde. Now we can use multiple reagents. So the first reagent is we can add copper or silver or gold at 300 degrees Celsius. 300 degrees Celsius. Second one, PCC and a non-polar solvent CH2Cl2 dichloromethane. It is a non-polar solvent. And third one, PDC non-polar solvent CH2Cl2. PCC means pyridinium chlorochromate. PDC means pyridinium dichromate. And fourth one, Fenton's reagent. Fourth one, Fenton's reagent. Fenton's reagent is H2O2 plus FeSO4. H2O2 plus FeSO4. And fifth one, open R oxidation. Fifth one, open R oxidation. Aluminum isopropoxide, aluminum isopropoxide and acetone. Aluminum isopropoxide and acetone. So this is a open R oxidation reagent. And the next one, Collins reagent. Collins reagent. CrO3 dot 2 pyridine. Collins reagent. And next one, NBS. NBS. And next one, MnO2. MnO2. MnO2 specialty is only for allylic and benzylic alcohols. Only for allylic and benzylic alcohols. Not for other alcohols. Only for allylic and benzylic. So we can add any one of these reagent to convert primary alcohol to aldehyde. If any molecule having the primary alcohol, if you want to convert into aldehyde, we can use any one of these reagent. PCC, the full form of PCC is pyridinium chlorochromate. Chlorochromate. So it is a pyridinium structure. Pyridinium chlorochromate. Next one is PDC. Full form is pyridinium dichromate. Pyridinium dichromate. Pyridinium dichromate. Like potassium dichromate, here we write the pyridinium dichromate. It is a pyridinium and a dichromate. Cr2O7. Pyridinium dichromate. To convert primary alcohol directly into carboxylic acid, or to convert secondary alcohol into corresponding ketone, so we can use any one of these reagent. First one, KMnO4. We can use heat condition or acidic medium condition or basic medium condition. Second one, dichromate, K2Cr2O7. Generally dichromate we use in acidic medium. And third one, chromic acid, H2CrO4, CrO3 plus H2O, Fourth one, PDC, water, polar solvent. Fifth one, PCC, water, polar solvent. And sixth one, Jones reagent. And the Jones reagent is CrO3 aqueous H2SO4. CrO3 aqueous H2SO4. So Jones reagent having some exception, so we will discuss it later on. So to convert primary alcohol into acid directly, or to convert to secondary alcohol to ketone, we can use any one of these reagent. And for ketone especially, we can use previous reagents and present reagents. Both we can use. First point. Next, primary alcohol to aldehyde, chromium plus 6 in anhydrous medium. If we use anhydrous medium, that means non-polar solvents, we get aldehyde. Suppose same primary alcohol, Cr plus 6, hydrous medium like water, the answer is carboxylic acid. So chromium plus 6 anhydrous medium aldehyde, chromium plus 6 hydrous medium carboxylic acids. Alcohol with copper, silver, gold at 300 degrees Celsius. So primary alcohol will be converted to aldehyde, secondary alcohol will be converted to ketone, but the tertiary alcohol converts into stable alkene. It is also an example of dehydration. Dehydration. In the first two cases, dehydrogenation. In the first two cases, dehydrogenation. In the third case, dehydration. For example, it is a primary alcohol. It is a primary alcohol. When the primary alcohol treated with copper, silver, gold, it converts into aldehyde. The primary alcohol carbon converted into aldehyde. So here what we have done, we remove the hydrogen from here and we remove the hydrogen from here. So minus H2. So మనం H2 ని remove చేసాం. That's why it is a dehydrogenation. Next example, it is a secondary alcohol. Secondary alcohol. So at the secondary alcohol also we remove the H2 and we get finally ketone. So by removal of hydrogen we get the ketone. It is a tertiary alcohol. It is a tertiary alcohol. So tertiary alcohol, no oxidation. So that's why here what we have to do, we have to do dehydration, alpha, beta, beta. It is a beta elimination. So we get two types of alkenes. One alkene like this. Suppose dehydration takes place here. Another alkene like this. Suppose dehydration takes place here. Among these two, this double bond has 5 hyperconjugation and this double bond has 9 hyperconjugation. Therefore, it is a stable alkene. Therefore, it is a stable alkene. That's why it is a major product. Stable alkene is a major product. Alcohol with copper, silver, gold. Primary alcohol aldehyde. Secondary alcohol ketone. This is an example of dehydrogenation. And tertiary alcohol dehydration takes place. Stable alkene is a major product. Jones reagent. Jones reagent. Suppose Jones reagent we are considering primary alcohol which is benzylic or allylic. The answer is aldehyde. The answer is aldehyde. Primary alcohol which is benzylic or allylic. The answer is acid. So aldehyde at low temperature and carboxylic acid at room temperature or above room temperature. Secondary alcohol will be converted to ketone at any temperature. Ketone at any temperature. Because secondary alcohol cannot undergo further oxidation. It undergo only up to ketone only. Now, simple primary alcohol other than benzylic allylic. So, primary alcohol, the answer is carboxylic acid. The answer is carboxylic acid. So these are the four conditions we have to remember before solving Jones reagent related questions. Primary allylic benzylic alcohols, low temperature aldehyde. Primary allylic benzylic alcohols, room temperature, above room temperature acid. Secondary alcohol ketone and primary alcohol acid. For example, this reactant treated with Jones reagent. This reactant treated with Jones reagent. So Jones reagent is CrO3 aqueous H2SO4. CrO3 aqueous H2SO4. Sometimes it also contains acetone. CrO3 acetone aqueous H2SO4. So here it is a primary alcohol and which is allylic alcohol. Primary and allylic. And temperature 0 degrees Celsius, which is low temperature. Low temperature. So we have discussed already primary allylic alcohol, low temperature. So it will be converts into aldehyde. Therefore, corresponding answer we should write, and this carbon will be converted to aldehyde. So it is a primary alcohol converted to aldehyde. Now the same compound treated with the Jones reagent at room temperature. So at room temperature, the same carbon will be converted into carboxylic acid. The same carbon will be converted into carboxylic acid. Next example, secondary alcohol. So secondary alcohol, there is only one possibility. Whether we use low temperature or high temperature, secondary alcohol will be converted into ketone. Secondary alcohol will be converted into ketone. Next one, primary alcohol, simple primary alcohol, or you can say aliphatic primary alcohol. When it is treated with a Jones reagent, whether it is a low temperature or high temperature, this primary alcohol carbon will be converts into corresponding carboxylic acid. We have to add one more carbon. Yeah. So this carbon 1, 2, 3, 4, 5. 1, 1, 2, 3, 4, 5. So the first carbon, primary alcohol carbon, that is converted into carboxylic acid. It's about the Jones reagent. PCC and PDC. So PCC full form is pyridinium chlorochromate. Chlorochromate. And PDC, pyridinium dichromate. Pyridinium dichromate. So PCC structure is pyridinium. It is the structure of pyridinium chlorochromate. And pyridinium structure is, it is like potassium dichromate, pyridinium taken twice, Cr2O7, pyridinium dichromate. So when we are using these reagents, primary alcohol will be converted into aldehyde. Secondary alcohol converts into ketone. Tertiary alcohol, no oxidation. Tertiary alcohol, no oxidation. Now we are discussing about the exception. Suppose second tertiary allylic alcohol is present. It is a tertiary allylic alcohol. When it is treated with PCC or PDC, so here what happens? Here the tertiary alcohol ionizes, form carbocation, and because of resonance, we get another carbocation, and this carbocation finally converts into secondary alcohol. So in the presence of PCC or PDC, the alcohol can undergo isomerization. So tertiary alcohol undergo isomerization and converts into secondary alcohol through SN1 mechanism, and this secondary alcohol undergo oxidation, and this secondary alcohol undergo oxidation. It is a final answer. Similar example, cyclopropane. So cyclopropane also behaves like alkene. So it undergo oxidation like this. when we use PCC or PDC. So initially carbocation is formed, and this carbocation forms stable C plus like this because of the ring opening. So because of the ring opening, we get the corresponding structure like this. Now it converts into corresponding stable C plus. Now it is finally combined with alcohol. So tertiary alcohol converts into secondary alcohol. Finally, it gives the corresponding product ketone. So initially the tertiary alcohol undergo isomerization and converts into ketone. Primary alcohol aldehyde, secondary alcohol ketone, tertiary alcohol no oxidation. But if the tertiary alcohol is allylic alcohol, it undergo isomerization, converts into secondary alcohol, finally it gives ketone. Potassium permanganate, heat H plus or OH minus or potassium dichromate acidic medium. The first example, the benzene next carbon is benzylic, and this hydrogen is benzylic hydrogen. When benzylic hydrogen is present, the entire carbon chain will be converted into carboxylic acid. The entire carbon chain will be converted into carboxylic acid. In the benzene next carbon, there is no benzylic hydrogen. Then two possibilities are there. One possibility, no reaction. Or we have to oxidize benzene ring. So benzene ring undergo oxidation. In the next example, we are having two benzylic carbons, but here benzylic hydrogen is present. Therefore, if benzylic hydrogen is absent, that carbon is unaffected, and the benzylic hydrogen carbon will be converted into carboxylic acid. If benzylic hydrogen is absent, no oxidation. If benzylic hydrogen is present, the entire carbon chain will be converted into carboxylic acid. Next example, it is having two benzylic carbons and benzylic hydrogen is also present. Therefore, the entire chain will be converted into, at this carbon, COOH, at this carbon, COOH, because of the benzylic hydrogen. Next example, benzene next carbon, benzylic carbon, benzylic hydrogen, benzene next carbon, benzylic carbon, benzylic hydrogen. The entire side chain, carbon chain, will be converted into corresponding COOH group. And this molecule common name is phthalic acid. Next example, benzene next carbon, alkene. When alkene is present, the entire chain will be converted into carboxylic acid. Next example, benzene next carbon, triple bond. Again, the entire carbon chain will be converted into carboxylic group. Next example, benzene next carbon, it can be primary alcohol, secondary alcohol, tertiary alcohol, the entire chain will be converted into carboxylic acid. The entire chain will be converted into carboxylic acid. Benzene next carbon ketone. So it is a aromatic ketone. Aromatic ketone. So in this case also the entire ketone chain will be converted into carboxylic acid. The entire ketone chain will be converted into carboxylic acid. Next molecule quinoline. Next molecule quinoline. In the quinoline, pyridine is deactivated. Pyridine is deactivated. That's why pyridine is unaffected. Pyridine is unaffected. So here simply we can say benzylic hydrogen, like this we can consider. So simply both carbons will be converted into carboxylic acid. Both carbons will be converted into carboxylic acid. Alkene treated with KMnO4. So simply we have to dissociate the alkene pi bond, and in this case left molecule, left group converted into carboxylic acid and right group also converted into carboxylic acid. And the next alkene, again we have to dissociate the double bond. The left group will be converted into carboxylic acid, but the right group will be converted into ketone. But the right group will be converted into ketone. When alkyne treated with the KMnO4 K2Cr2 conditions, so we have to break the triple bond and we have to write left group will be converted into carboxylic acid and a right group also converted into carboxylic acid. When glycol, so it is a glycol compound, more than one OH group is present, glycol. In 1,2 glycols also called vicinal diol. Vicinal diols. When vicinal diols treated with the KMnO4 K2Cr2 conditions, so it will dissociate and the left group will be converted into carboxylic acid in this structure and the right group also converted into carboxylic acid. Sometimes it depends on the group. Sometimes it undergo ketone and sometimes it undergo acid. Because of the CH bond, both are converted into carboxylic acid. Next one, alpha hydroxy ketone. It is a alpha hydroxy. So in this case also we have to break the corresponding sigma CC sigma bond. So because of CH bond, left group converted into carboxylic acid and a right group, there is no other possibility, that will also undergo into carboxylic acid. Next example, diketo. Next example, diketo. In the diketo, 1,2 diketo or alpha diketo. So we have to break the CC bond in between the CO groups and the left group converted into carboxylic acid and the right group also converted into carboxylic acid. When we take the ketone, and ketone with KMnO4 or K2Cr2O7, generally no reaction. But when we use drastic conditions, that means very high temperature with these reagents, when we use very high temperature, they undergo oxidation by breaking the, suppose it is a CO carbon. So for simplicity, for better understanding, I am writing 1 comma 2 and 1 comma 2. You can break any one of these bond. And left group converted to carboxylic acid and right group converted to carboxylic acid. Left group converted to carboxylic acid, right group also converted to carboxylic acid. Since it is a formic acid and formic acid always undergo oxidation and converts into CO2. Formic acid always undergo oxidation, converts into CO2. Suppose in the ketone, two different groups are present, both sides. It is called unsymmetrical ketone. Unsymmetrical ketone because ketone is connected to two different groups. It is a 1 comma 2 carbon. It is also 1 comma 2 carbon. In this case, we can break CC bond both sides. So the reaction takes place only at very high temperature. Very high temperature. So suppose if we break this bond, the left group converted to acetic acid and the right group also converted to acetic acid. Another possibility, we can break this bond also. The left group converted to formic acid and which further undergo oxidation to CO2, and the right group converted to propionic acid or propanoic acid. The right group converts into propionic acid or propanoic acid. So among these two possibilities, we have to consider this is as major product. This is a major product. It is based on the Popoff's rule. It is based on the Popoff's rule. And the Popoff's rule is the CO group will be attached with will be attached with will be attached with less carbon chain. Less carbon chain. Now what is the meaning of less carbon chain? It is a less carbon chain. Less carbon chain. It is a more carbon chain. More carbon chain. Suppose if we take another example, suppose ketone is given like this and we are using KMNO4 or K2Cr2O7 at very high temperature. Very high temperature. So here two possibilities are there, but I am writing major product. It is a 1, 2, it is a 2, it is a less carbon chain, it is a more carbon chain. So majorly we have to break the bond here. Majorly we have to break the bond here. So left group converted into CH3COOH and the right group converted into COOH, CH2, CH2, CH3. That means butyric acid or butanoic acid. So in this case, the COOH group, here the CO group, the COOH group, here the CO group will be attached with less number of carbon. So generally we do not consider oxidation for ketones. If it is in the question, based on the question, we have to understand if it undergoes oxidation, what are the products? If it undergoes oxidation, what are the products? Then we have to do the oxidation. Otherwise, no reaction. If it undergoes, what are the products? If they're asking, then write the answer according to Popoff's rule. Otherwise, no reaction. Aldehyde from toluene derivative. So we use a reagent CrO3 and acetic anhydride. Acetic anhydride. CH3CO taken twice oxygen. The structure is CH3 C double bond O C double bond O CH3. First we add CrO3 acetic anhydride and next we add hydrolysis condition H3O plus heat or OH minus heat. It is a hydrolysis condition. For example, toluene treated with CrO3 and acetic anhydride. So here what we have to do, it is a benzylic carbon. At benzylic carbon, add two ester groups O C double bond O CH3 O C double bond O CH3. We have to add two ester groups. It is called benzylidene diacetate. Benzylidene diacetate. acetate. This compound undergo hydrolysis either in basic medium or in acidic medium. Either in basic medium or acidic medium. So here what we have to do, we have to break the corresponding CO bond at the indicated position. So at this position we have to break, and here we have to add hydrogen, and here we have to add OH group. Here we have to add hydrogen, and here we have to add OH group. Therefore, the product is benzene CH OH group, OH group, and it is CH3COOH, CH3COOH, and it is also CH3COOH. Now this is hydrated form, and hydrated form immediately loses water. Hydrated form loses immediately water and finally converts into aldehyde. Finally converts into aldehyde. So toluene on addition of CrO3 acetic anhydride after hydrolysis finally converts into aldehyde. Sometimes they don't give the hydrolysis in the exams, so we have to understand the question and accordingly we have to solve the question. Second example, benzene CH3 para position NO2. Para nitrotoluene. When para nitrotoluene treated with CrO3 acetic anhydride followed by hydrolysis, so we can write answer directly. The CH3 group converted to carboxylic acid. Sorry, not carboxylic acid. The CH3 group converted to aldehyde. The CH3 group converted to aldehyde. So para-nitrobenzoic acid. Para-nitrobenzoic acid. So whenever you want to convert the benzylic next carbon CH3, into CHO, we can use this reagent. Ethod reaction. In the Ethod reaction, the reagent is CrO2Cl2. It is called chromyl chloride. Chromyl chloride. And the solvent generally non-polar solvent, carbon disulfide, and then hydrolysis. We can use acidic medium hydrolysis, or we can use basic medium hydrolysis. For example, toluene, treated with CrO2Cl2 in carbon disulfide solvent. At the benzylic carbon, we should write two groups. So one group is OCr OH Cl. Another group, same group, Cr Cl OH. So same groups two times, and then it undergo hydrolysis. Simply we should write the answer, benzene CH double bond O. So this entire CH group by the hydrolysis condition converts into CHO. Suppose if we take para-nitrotoluene treated with CrO2Cl2 carbon disulfide followed by hydrolysis, simply the CH3 group converts into CHO. The CH3 group converts into CHO. For example, paraxylene treated with CrO2Cl2 in chloroform solvent followed by hydrolysis. If we use one equivalent, we can write answer simply. The CH3 group will be converted to CHO. The CH3 group will be converted to CHO. Getterman-Koch reaction. Reagent is carbon monoxide HCl in the presence of AlCl3 or ZnCl2. Any Lewis acid we can use. From this combination, we get electrophile Hc double bond O plus formyl electrophile group. Formyl electrophile group. Simply we can write HCO plus. It is our electrophile. Suppose if we treated benzene with carbon monoxide HCl ZnCl2. So from this combination we get electrophile HCO plus, and simply it is an aromatic compound and electrophile. So we have to write according to electrophilic aromatic substitution. So simply here electrophile will be substituted in place of H plus. It is electrophilic aromatic substitution. Suppose if we take toluene, it is treated with carbon monoxide HCl ZnCl2. From this combination we get electrophile HCO plus, and it is an example of electrophilic aromatic substitution. And here the CH3 group is OP directing group. Therefore we get mainly two products. One is ortho position CHO and another one is para position CHO. Para position CHO. Among these two, para product is major. Among these two, para product is major. So this reaction is Getterman-Koch reaction. Baker process. When alkene treated with PDCl2, CuCl2, O2 and water, at the double bond carbon, we have to remove the alkene pi bond and we have to add double bond O like this. So it is acetaldehyde. It is acetaldehyde. Second example, when propene treated with PDCl2, CuCl2, O2, H2O, so we have to remove the alkene pi bond and add double bond O. Now here two possibilities are there. We can add double bond here and we can also double bond O here. So we are writing the two products. First product is CH3, C double bond O, CH3. It is a ketone. Second product is CH3, CH2, CH double bond O. It is aldehyde. It is aldehyde. Among these two, ketone is major product. Among these two, ketone is major product. When this alkene treated with PDCl2 and CuCl2, so there are two possibilities. So we can write the first possibility. At this carbon, we can add double bond O, and at this carbon, we can add double bond O. And among these two, so major cannot be decided. So if ketone and aldehyde both are forming, we can say ketone major. If both are aldehydes and both are ketones, in this case we generally do not decide major product. When alkene treated with PDCl2, CuCl2, O2 and water, we have to add double bond O at alkene position, and this carbon is tertiary carbon, so we cannot add double bond O here because carbon is already having the three bonds. If we add double bond extra, then carbon gets five bonds, so that is not possible. There is only one possibility. There is only one possibility, that is ketone like this. So we can add double bond O here. So we cannot add a double bond O at this position. This is not at all possible. This is not at all possible. So in this case, we are getting single compound as major product. Oxo process. When propene treated with carbon monoxide, H2 and cobalt carbonyl, it is a complex of cobalt, and in this complex carbon monoxide is a ligand. So the total reagent is carbon monoxide, H2, cobalt carbonyl. So here we are having alkene carbon. So it is a primary carbon, it is a secondary carbon. So in this case, what we have to write, at the secondary carbon add CHO, at the secondary carbon add CHO, at primary carbon add CHO. We have to add extra carbon. So we are getting two products here. Among these two, so we have to follow this order: primary, secondary, tertiary. In the oxo process, we have to follow primary, secondary, tertiary. Therefore, it is a major product. Similarly, second alkene treated with carbon monoxide, H2, and cobalt carbonyl, we get two compounds. So one compound is at tertiary carbon, CHO. Another compound is at secondary carbon, CHO. It is a tertiary carbon, it is a secondary carbon, and we know the order: primary, secondary, tertiary. Therefore, secondary carbon is major product. Secondary carbon is major product. Tollens reagent. Tollens reagent is ammonical silver nitrate. Ammonical silver nitrate. Simply we can write Ag NH32 plus OH minus, and sometimes they will give like silver nitrate plus ammonia solution or ammonium hydroxide solution. So at the end of the reaction, it converts into Ag. At the end of the reaction, it converts into Ag. So it is silver mirror. That's why it is also known as silver mirror test also. Next, Fehling solution. We are having two solutions: Fehling solution A, Fehling solution B. So Fehling solution A, CuSO4, and Fehling solution B, rock La salt. Rock La salt. And rock La salt is sodium potassium tartarate. Sodium potassium tartarate. And structure of sodium potassium tartarate is COO minus Na plus CHOH CHOH COO minus K plus. So it is a sodium potassium tartarate. Benedict solution, again two types: Benedict A, Benedict B. So Benedict A, CuSO4, and Benedict B, sodium citrate. Sodium citrate. Sodium citrate. And the structure is CH2 COONA COH COONA CH2 COONA. So it is a sodium citrate. All the solutions are basic in nature. Tollens, Fehling, Benedict, all are basic in nature. And in both cases, Fehling and Benedict, in both cases, the Cu plus 2 at the end of the reaction finally converts into Cu2O. It is a red brown PPT. Red brown PPT. If Fehling and Benedict participate in the reaction, they converts finally into red brown PPT of Cu2O. In the Tollens reagent, silver mirror. In the Fehling and Benedict solution, red brown PPT if they undergo the reaction. Now the first example is aldehyde. To aldehyde, if I add Tollens reagent or Fehling solution or Benedict solution, the entire CHO group will be converted to COO minus. The entire CHO group will be converted to COO minus. COO minus. Now here we are having one exception, and the exception is aromatic aldehydes. aromatic aldehydes, Tollens reagent, answer aromatic COO minus, failing solution or Benedict solution, no reaction. Failing solution or Benedict solution, no reaction. Aliphatic aldehyde, we can use Tollens reagent, we can use failing solution, we can use Benedict solution. But for aromatic aldehydes, only Tollens reagent oxidages and failing solution and Benedict solution, no oxidation. First example. Second example, hemiacetal. Second example, hemiacetal. It is a hemiacetal. Since it is a basic medium, hemiacetal undergo dissociation and converts into aldehyde plus alcohol. Converts into aldehyde plus alcohol. So we have to remove these two groups. We have to remove these two groups. Now this aldehyde undergo oxidation and converts into corresponding carboxylate. Corresponding carboxylate. It is second functional group. And the third functional group is alpha hydroxyketone. Third functional group is alpha hydroxyketone. It is a alpha position. So alpha hydroxyketone. In this case, the only alcohol group will be oxidized and corresponding ketone will be formed. Finally, we are getting diketo compound. We can also say alpha diketo compound. Alpha diketo compound. It is third functional group. And the fourth functional group is formic acid. Formic acid will be oxidized to CO2. Since it is a basic medium, sometimes we can write it as CO3 minus 2. And the remaining carboxylic acids, no reaction. Remaining carboxylic acids, no reaction. Next one, N-hydroxyamine. So it is a amine group and it is hydroxy. Therefore, N-hydroxyamine. So here the answer is simply the NHOH group similar to alcohol undergo oxidation and gives corresponding nitroso compound. Corresponding nitroso compound. Next example is RCOCH2OH. RCOCH2OH. It is a primary alcohol. It is a primary alcohol and it is a keto group. Keto group. So మనకి ప్రైమరీ పొజిషన్లో ఆల్కహాల్ ఉండాలి, నెక్స్ట్ కీటోన్ ఉండాలి. సో దిస్ కైండ్ ఆఫ్ మాలిక్యూల్ immediately undergo isomerization and converts into secondary alcohol and aldehyde. సో ఈ గ్రూప్ అనేది మనకి ఐసోమరైజ్ అవుతుంది. సో మనకి సెకండరీ కార్బన్ దగ్గర ఆల్కహాల్ వచ్చింది, ప్రైమరీ కార్బన్ దగ్గర CO గ్రూప్ వచ్చింది. Now it is aldehyde and aldehyde undergo oxidation. Therefore, final answer is corresponding COO minus. CHO is converted to COO minus. Tollens, failing, Benedict. So we have to remember these functional groups. One is aldehyde. In the aldehyde, aliphatic aldehydes will be oxidized to carboxylate. Aromatic aldehydes, no reaction. Second one, hemiacetal. Hemiacetal, in the presence of basic medium, converts into aldehyde plus alcohol. So we have to remove the H group and RO group. And then aldehyde converts into corresponding carboxylate. Next one, alpha hydroxyketone. In the alpha hydroxyketone, alpha hydroxy converts into CO. That means alpha diketo. Next example, formic acid undergo oxidation, CO2. In basic medium, we can write CO3 minus 2. But remaining carboxylic acids, no reaction. Next, N-hydroxyamine. So this is like alcohol type, undergo oxidation, So it is nitroso group. Next, RCOCH2OH, primary alcohol keto, undergo isomerization first, secondary alcohol aldehyde, and this aldehyde undergo oxidation converts into carboxylate. This aldehyde group undergo oxidation converts into carboxylate. Phenols oxidation. For phenols oxidation, we use the reagents Ag plus or Fe plus 3 or aerial oxidation or sodium dichromate, acidic medium, or we can use chromic acid. So these are the some of the oxidizing agents which oxidizes phenol and aniline both. For example, for example, phenol or aniline. So the answer is simply we get two products. One is double bond O, and another one is keto group, keto group. So first compound is orthoquinone, second compound is paraquinone, orthoquinone and paraquinone. This is the first example. Second example, benzene 1, 2 diol. It is also known as catechol. Catechol. So here 1, 2 position OH group. We can also consider NH2 NH2 also. The answer is simply only orthoquinone. We get only orthoquinone. Benzene 1, 4 position OH groups. It is called quinol. It is called quinone. Quinol. So here we get only paraquinone. Here we get only paraquinone. And here 1, 2 position OH group. So it is a catechol type. It is a catechol type. So here we get only orthoquinone. Here we get only orthoquinone. Next here 1, 4 position OH group. So it is a quinol derivative. So here we get only paraquinone. Here we get only paraquinone. And here phenol derivative. So ortho position is blocked. Therefore, there is only one possibility, paraquinone. There is only one possibility, paraquinone. So here, whenever the methyl group is present, the most preferable reagents are Ag plus, Fe plus 3 or O2. Whenever methyl group is present, Ag plus, Fe plus 3 or O2. Because if methyl group is present, if we use sodium dichromate, methyl also can be oxidized. Because if methyl group is present, methyl group can be oxidized with dichromate. V2O5 with benzene derivatives, vanadium pentoxide, generally the reaction takes place at 500 degrees Celsius. Suppose benzene treated with V2O5, so only these four carbons will appear and the corresponding product is like this. Only four carbons will appear. It is maleic anhydride. Maleic anhydride. Suppose naphthalene treated with vanadium pentoxide at 500 degrees Celsius. One benzene ring unaffected, second benzene ring converts into anhydride. And this compound name is phthalic anhydride. Phthalic anhydride. Suppose if we take alpha naphthol, V2O5 500 degrees Celsius, because of plus R group, this benzene electron density more, therefore electron density more, that corresponding benzene will be oxidized. If electron density is more, that will be oxidized. For example, benzene, benzene, and here NO2 group is present. Because of NO2, electron density is less because of minus R effect of NO2. Therefore, in this case, NO2 connected benzene unaffected and remaining benzene will be oxidized to corresponding anhydride form. Corresponding anhydride form. Reaction with HiO4, NaIO4, lead tetraacetate. HiO4, NaIO4, lead tetraacetate. HiO4 also known as periodic acid, and sometimes in the question it will be mentioned as periodic cleavage. So here the conditions are 1 comma 2 position OH groups, 1 comma 2 position OH groups, and we can also consider NH2 group also, NH2 group also. When you are using these reagents, so simply what we have to do, we have to break this bond, we have to break the CC bond, and this carbon undergo oxidation, this carbon undergo oxidation, and this carbon also undergo oxidation. So the first carbon converted into aldehyde, second carbon also converted into aldehyde. Second example, second example, 1 comma 2 position OH group, OH group. So in this case, 1 comma 2 position OH groups are there. We have to break the bond, and this carbon undergo oxidation and it will be converted into aldehyde, and this carbon also undergo oxidation. Answer corresponding aldehyde. Suppose the structure is tertiary alcohol and tertiary alcohol. Both are tertiary alcohols. And it is first carbon, second carbon. 1 comma 2 diol. In this case also, we have to break the CC bond. First carbon undergo oxidation. First carbon undergo oxidation. Second carbon also undergo oxidation. Second carbon also undergo oxidation. Like this. So both will be converted into ketone. Suppose one is aldehyde, another one is alcohol. In this case also, we have to break the corresponding CC bond, 1 comma 2 position. We have to break the CC bond. So it will undergo further oxidation, converts into formic acid. It is already in the aldehyde state. That's why we should write formic acid. And the second carbon converts into formaldehyde. Second carbon converts into formaldehyde. Suppose both are aldehydes, CHO, CHO. When you use these reagents, again 1 comma 2 position, we have to break the CC bond. It is already in the aldehyde state, therefore converts into formic acid. It is already in the aldehyde state, therefore converts into formic acid. Suppose the structure is keto group and keto group, 1 comma 2 position keto group. Again we have to break the CC bond. So the first carbon will be converted into carboxylic acid, and the second carbon also converts into carboxylic acid. Both carbons converts into carboxylic acid. For example, epoxide ring is present. So three-membered ring is epoxide, three-membered cyclic ether is epoxide. So here also we have to break the CC bond. We have to break the CC bond, and corresponding answer CHO, CHO. Simply we have to break the CC bond. We should write CHO, CHO. Now here the most important point is CH2OH, CH2OR, like this. Then here the oxidizable, this is oxidizable, but it is not oxidizable. It is not oxidizable. It is not oxidizable. Therefore, in this case, no reaction. In this case, no reaction. For example, CH2OH, CH2, CH2OH. In this case, 1 comma 2. So here it is not oxidizable. Not oxidizable. Not oxidizable. And again 1 comma 2. So here this 1 comma 2 bond is not breakable, and this 1 comma 2 is also not breakable. That's why no reaction. No reaction. Next example, CHO, CHOH, CH2OCH3. So in this case it is 1 comma 2. So both are oxidizable. We can break CC bond, but this group is non-oxidizable. This group is non-oxidizable. Therefore, the corresponding answer, first carbon converts into formic acid, second carbon converts into aldehyde, this carbon converts into aldehyde, and the remaining group as it is without affected. It is unaffected group. For example, CHO, CHOH, CH2OH. So it is 1 comma 2, it is oxidizable. 1 comma 2, it is also oxidizable. So both bonds are oxidizable. So we have to break the bond like this. So this carbon converts into formic acid, and this carbon converts into formaldehyde, and this carbon 2 times oxidation. So because of upside bond, 1 time oxidation, because of downside bond, 1 side oxidation. సో ఫస్ట్ బాండ్ బ్రేక్ అయితే ఆల్డిహైడ్ వస్తుంది ఆర్ కీటోన్ వస్తుంది, మళ్ళీ అగైన్ బాండ్ బ్రేక్ చేస్తే యాసిడ్ వస్తుంది. సో హియర్ ఆన్సర్ ఫార్మిక్ యాసిడ్. 2 టైమ్స్ బ్రేక్ చేసాం కాబట్టి ఇక్కడ ఫార్మిక్ యాసిడ్ వస్తుంది. ఫస్ట్ టైం బ్రేక్ చేస్తే సి డబుల్ బాండ్ ఓ, సెకండ్ టైం బ్రేక్ చేస్తే ఫార్మిక్ యాసిడ్. ఫర్ ఎగ్జాంపుల్ CHO, C double bond O, CH2OH. This molecule is undergoing periodic cleavage. 1 comma 2 CC bond breakable, 1 comma 2 CC bond breakable, because all are oxidizable functional groups. So first carbon converts into formic acid. Again the last carbon also undergo oxidation, converts into formaldehyde, and the middle carbon 2 times oxidation. It is already in the ketone state. So if it undergo first oxidation, acid type, second oxidation, CO2. Second oxidation, CO2. Next example, CHO, CHOH, 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 CH2OH. In this case also, so here this bond is oxidizable, this bond also oxidizable, this bond also oxidizable, and this bond also oxidizable. So first carbon converts into formic acid, second carbon 2 times oxidation, therefore converts into formic acid, third carbon 2 times oxidation, formic acid, fourth one 2 times oxidation, formic acid, fifth one 1 time oxidation, formaldehyde. 1 time oxidation, formaldehyde. For example, structure is given like this. Structure is given like this. So if you identify the structure, so this bond is oxidizable, this bond is oxidizable. Only these two bonds are oxidizable because one position OH, two position OH, one position OH, two position OH. Only these two bonds are oxidizable. So we have to break the bond like this. We have to break the bond like this. Therefore, corresponding answer, these groups are unaffected, these groups are unaffected, and this carbon one time dissociation, one time oxidation CHO, and this carbon also one time oxidation, it is one time oxidation, it is also one time, but the middle carbon two times oxidation. Therefore, answer formic acid. Two times oxidation, therefore answer formic acid. So these are the examples of per iodic cleavage. Bromine water with aldoses and ketones. So bromine water means Br2H2O or HOBr. With this reagent, only aldoses react. Aldoses react, and aldoses will be converted to aldonic acid. Aldonic acid. And ketones, no reaction. Ketones, no reaction. So here bromine oxidizes aldoses, and ketones, no reaction. After the reaction, if bromine water participate in the reaction, the bromine will be decolorized. The bromine will be decolorized. That means aldoses are reacting with bromine water. Therefore, aldoses decolorizes bromine water, bromine water or bromine, but ketone, ketones or ketones, but ketones do not. Ketones do not. For example, it is a structure of glucose. It is a structure of glucose, and if it undergo reaction with bromine water, only this CHO group will be oxidized. Remaining are unaffected. Only this CHO will be converted to COOH. COOH. So it is a OH group. It is a OH group. So the remaining groups are unaffected. The first compound is glucose, D-glucose. Second compound is D-gluconic acid. Gluconic acid. So glucose is a is one of the example in the aldoses family. Gluconic acid is one of the example in aldonic acid. Gluconic acid is one of the example in aldonic acid. When glucose treated with bromine water, the CHO group will be converted to COOH. So whenever the molecule is like this, it is aldoses. Simply the CHO group will be oxidized. The CHO group will be oxidized. So it is a aldose and it is a aldonic acid. Aldonic acid. Suppose fructose, it is a structure of fructose. It is a structure of fructose. It is a D-fructose. D-fructose. D-fructose with bromine water. D-fructose with bromine water. No reaction. And in the fructose, it is a main group. So if the molecule is like this, if the molecule is like this, it is called ketones. Ketones. Ketones, bromine water. Ketones, bromine water, no reaction. Ketones, bromine water, no reaction. Bromine water, next example is hemiacetal. Hemiacetal will be converted into corresponding ester. In case ఒకవేళ cyclic ester అయితే, that is called lactone. For example, so this carbon is hemiacetal. This functional group is hemiacetal. So when we added bromine water, so simply it will be converted to lactone. It is a hemiacetal. This portion is hemiacetal portion. It will be converted into cyclic ester. It is known as lactone. It is known as lactone. Suppose if we take glucose, it is another form of glucose. It is another form of glucose. Another form of glucose. When we add bromine water, it is a hemiacetal part. The remaining groups are unaffected. The remaining groups are unaffected. The remaining groups are unaffected. Only this portion is oxidized to lactone. Only this portion is oxidized to lactone. So bromine water can oxidize aldoses to aldonic acid and cyclic hemiacetal to lactone. So these are important reactions for bromine water.